Welcome to our presentation. My name is Christina Insam and I'm a PhD student at the Technical University of Munich. The results that I'm going to present are the outcome of a research stay that I made at the University of Connecticut with Dr. Richard Christensen, Matthew Stevens, and Michael Harris. During this project, we worked on real-time hybrid substructuring for shock applications, and in particular, our focus was on effective actuator control schemes. Let's start with a quick recap of real-time hybrid substructuring, short RDHS. RDHS is a cyber-physical approach where numerical simulation and experimental testing are combined to analyze the dynamics of the coupled system. Motion and force information is exchanged in real time at a fixed sampling rate. In this project, we wanted to investigate the applicability of RDHS testing for shock applications. Shock phenomena are characterized by a rapid change in loading conditions. Our objective was to determine the advantages as well as the challenges associated with RDHS testing of shock phenomena. So the dynamical system that we selected for these investigations can be seen here. Basically, this is a pendulum that hits a mass spring damper system when it swings down. To model the contact interaction is already challenging for this very simple system. This is because dynamical properties of the contact partners and the contact dynamics are required. So it's easier to capture the contact forces in the experimental substructure. One might be interested in seeing how the interaction force profile differs for different system parameters of the mass spring damper system. To be able to change the parameters easily, the mass spring damper system should therefore be in the numerical substructure. So the coupled dynamical system is split accordingly. The pendulum is part of the experimental substructure, and this hammer is mounted with a pivot joint, and it can be locked at its initial angle with a locking mechanism. To couple the substructures, we need a transfer system. In our case, this consists of an actuator, which is an electrodynamic shaker, and then we need to measure the interaction forces as well as the acceleration of the shaker tip, which was done with an impedance sensor, and we required a digital signal processor, which was a speed-code real-time performance platform in our case that ran at 20 kHz. All right, so the signal flow in this RDHS setup is as follows. First, the pendulum is at rest at its initial angle. Then we pull the locking mechanism such that the pendulum starts swinging. When the pendulum strikes the shaker, a force can be measured and the RDHS test execution starts. This external force is used to solve the equation of the mass spring damper system. The mass spring damper system then outputs a motion command for our electrodynamic shaker. In our case, this is an acceleration command. We selected the acceleration command because we use an amplifier that outputs current, and the shaker acceleration is proportional to a current input. As you can see, there is also a force compensation module in our RDHS block. And let me explain the reason for this force compensation block on the next slide. The impedance head that we used is a standard sensor by PCB. When we performed an RDHS test with the setup that I've just presented to you, then we see the following measured force. There is a double hump force profile during the interaction period, and the interaction period takes about 12 milliseconds. And after that, we see a small oscillating force. This force comes from an oscillation of the shaker, and remember that the shaker moves according to the simulation of the mass spring damper system, so the mass spring damper system vibrates with its eigenfrequency after the interaction period. However, since there are no interaction forces anymore, we expected that the force would be zero. So we asked ourselves why we still measure something and looked into the sensor drawing. Here you can see the piezo discs that measure the acceleration and force data, and this upper end is attached to the shaker, and this side here is the side which is hit by the pendulum. So there is this portion of the sensor that has inertia and creates these forces. And these forces should be compensated in our setup. So we needed to find out how heavy this portion of the impedance sensor is that creates these inertial forces. So we measured the transfer function of the impedance head, and we did this by exciting the shaker with band-limited white noise and recorded the acceleration and force signals. When we plot the measured transfer function, we can see a constant magnitude and an almost constant phase of 180 degrees. This supports our hypothesis that the oscillations are based on the inertial forces of parts of the impedance sensor. From the magnitude of the transfer function, we could see that the mass is approximately 8.5 grams. So we compensated the measured forces with these inertial forces and performed another RDHS test. The compensated force values are shown here in orange. After the impact phase, the force now remains zero, and this is the intended behavior. So this was the RDHS setup that we proposed. I will now go into detail about the implementation of the controller that we implemented for the shaker. First, we started with a minimum phase inverse compensator. This is a kind of feed-forward controller that uses the inverse of a measured transfer function. If the plant is modeled accurately, we can achieve very good tracking performance with this kind of controllers. In our case, the plant comprises the amplifier and the electrodynamic shaker. To create this inverse compensator, we have to measure the transfer function. We did this using band-limited white noise, which was used as the input for the plant UC, and we measured the acceleration output XM double dot. Then we approximated the measured transfer function. This approximated transfer function will in the next step be inverted and used as the inverse compensator. This inverse compensator should be stable, which means that the compensator should not have or should only have left-hand side poles. Therefore, the approximated transfer function must not have right-hand side zeros. The so-called minimum phase part of a transfer function only contains left-hand side zeros, and therefore we selected to take the minimum phase part of our approximated transfer function. Here you can see the measured transfer function in blue and the minimum phase transfer function in orange. The minimum phase part of the transfer function still contains the correct magnitude over the whole frequency range. However, the minimum phase part has a phase error. There is a large discrepancy between the measured transfer function and the minimum phase model that is used as inverse compensator. So we expect that the phase error will still be very large, and we need to enhance this minimum phase inverse compensator by an additional compensator. We decided to use Iterative Learning Control. This is a control scheme that is used for robotic tasks that are performed repeatedly. If the same task is performed repeatedly and the controller does not change, the same error is made in every iteration. So the idea in Iterative Learning Controller is to find a feed-forward signal that the error decreases from iteration to iteration. The feed-forward signal is generated based on the feed-forward signal from the previous iteration, a learning function L, and the error from the previous iteration. The filter Q that you can see here is a robustness filter, which is usually a zero-phase low-pass filter. There are different possible choices for the learning function L, and we chose a rather simple implementation, which is that L is just a proportional gain. The application of Iterative Learning Control to improve the tracking performance in RDHS tests has been proposed in one of our former papers, which is cited here. In this paper, we showed that the phase tracking properties improved during learning. So we hypothesized that the combination of Iterative Learning Control with the minimum phase inverse compensator might be effective for our intended RDHS test. So to wrap up, you see the resulting control scheme that we used for the RDHS test, which consists of the model-based inverse compensator and the Iterative Learning Control. Model-based inverse compensator is a pure feed-forward controller, and Iterative Learning Control is kind of a feedback controller in iteration domain. On this video, I want to show you the test execution of one RDHS test, where the eigenfrequency of the simulated mass spring damper system was 50 Hz. First you see it in real time, and now you see it slowed down. So this video should show you that the test execution is pretty short and requires a quick reaction. I'm aware that you can unfortunately not really see the vibration because the video was taken with a normal smartphone camera and the vibration is too quick for that. But we can look at the results in time domain. So first I want to show you that Iterative Learning Control converged. This means that the error becomes smaller and smaller as the number of iterations increases. For the RDHS test that we performed, the eigenfrequency of the mass spring damper system was 100 Hz with a damping ratio of 5%. The pendulum initial angle was 15 degrees. In the first iteration, only the minimum phase inverse compensator was active. And during the interaction period, we see a large overshoot of the measured acceleration, and during the free vibration response, we see a large phase delay. This first overshoot is due to the flexibility of the shaker at the hammer strike. So at iteration 7, the tracking has improved a lot. First of all, the overshoot is much smaller, and secondly, the delay is much smaller as well. Here we plotted the acceleration error, which is just the deviation between the commanded and the measured acceleration. We can observe that the error decreases from iteration to iteration. But this figure also reveals that in the first 1.2 milliseconds, the acceleration error is always the same and it does not matter whether the shaker is activated or not. This initial acceleration is always the acceleration due to the compliance of the shaker. And from this it is also obvious that there is some kind of time delay between the commanded acceleration and the measured acceleration. And we are pretty certain that the source for this delay is in our analog amplifier. Nonetheless, we continued with experiments and wanted to see whether we can see changes in the interaction force depending on the selected eigenfrequency of the mass spring damper system and the mass ratio. The mass ratio is the ratio between the numerical mass and the experimental mass. In 2 experiments, the mass was 3 times heavier than the pendulum mass, and in the third experiments, they were equally heavy. The eigenfrequency of the mass spring damper system was either 50 Hz or 100 Hz. The interaction force profiles differ depending on the system parameters. This is what we expected and hope to see in the RDHS experiment. We can see that for the system with 50 Hz, and there is a double hump profile, and the interaction period is quite long. In the system with 100 Hz and the mass ratio of 3, there is only one force peak. But for the mass ratio of 1, we can see a double hump profile again. Unfortunately, we cannot yet be certain if these force profiles are the real profiles that we could expect if this whole system was set up experimentally, because we have the delay in the first 1.2 milliseconds. But we are already happy to see the differences in this preliminary test. So to conclude, we performed an RDHS test of a hammer which is swinging like a pendulum and impacting a mass spring damper system. And we used an impedance head to measure the accelerations and interface forces. And to get the correct measurements, we had to compensate the inertia forces. For actuator compensation, we used a combination of minimum phase inverse compensator and iterative learning control. And we could see that the interaction force profiles can be studied. Apart from that, we could define several challenges in RDHS testing of shock applications, which includes the delay of the amplifier. So we should need to predict somehow when the hammer strike will happen, such that we can already start sending the motion command 1.2 milliseconds ahead. Then there is the compliance of the shaker, and to see whether it still works to investigate the interaction, the interaction force profile and so on, we need to generalize this in more complex systems. This is the list of references. And we thank you very much for listening to this talk. We are excited to have a discussion with you at this year's conference, and take care. Bye.